very important result. For two matrices A and B of the type m by n, the following statements are equivalent. First, B is obtained from A by applying the row operations. Second, there exists a non-singular matrix P such that B is equal to PA. Third, row space of A is equal to row space of B. And fourth, the row echelon forms of A and B are equal. So we have to prove all these statements to be equivalent. That means we have to prove second statement from the first statement, then third statement from the second statement, then fourth statement from the third statement, and then first statement from the fourth statement. So before starting with the proof, let's recall few results. First, if A be m by n matrix such that B is obtained from A by applying the row operations, then there exists a non-singular matrix P such that B is equal to PA, right? Second, let A be m by n matrix and P be a non-singular matrix, then row space of PA is equal to row space of A, provided this P should be non-singular, right? Third, if B is obtained from A by applying the row operations, then row space of A is equal to row space of B. Next, please note this very important remark. If A and B are two matrices of the same type such that row space of A is equal to row space of B, and if C and D are matrices in a row echelon form, that is, if C matrix is obtained from A by applying the row operations and D matrix is obtained from B by applying the row operations, then this C and D are equal, right? This result also we are going to use in the proof. So let's start with the proof. First, what is given to us? That B is obtained from A by applying the row operations, right? And we have to prove that B is equal to PA. Means we have to prove that there exists a non-singular matrix P such that B is equal to PA, right? Okay. Now this B is obtained from A by applying the row operations, right? Okay. Suppose even with the elementary row matrix obtained from A by applying the first row operation. Then further again by applying the row operations we obtained E2, then we obtained E3, so on up to ER, right? And so by applying the so many row operations we obtained all these row elementary matrices, right? So let corresponds to pre-multiplication by the row elementary matrices in this E1, E2, E3 up to ER order. Thus, B is equal to multiplication of all these matrices, ER, so on, E3, E2, E1 into A, right? Which is equal to, let's take all this multiplication of these row elementary matrices to be as P, right? Where P is equal to multiplications of all these matrices, that is ER multiplied with so on E3, E2 multiplied with E1, right? So further this B is equal to, for this I am writing P and then A, right? So we get B is equal to PA. Now since this E1, E2, E3 so on up to ER, all these row elementary matrices are non-singular, right? So therefore their multiplication is also non-singular, and because P is equal to multiplication of all these matrices, so P is also non-singular. Thus we have shown that the existence of non-singular matrix P such that B is equal to PA from this statement. Second, it is given to us that suppose there exists a non-singular matrix P such that B is equal to PA, then we have to prove that row space of A is equal to row space of B. Now, because there exists a non-singular matrix P such that B is equal to PA, so therefore row space of B is equal to row space of PA. This is the result. And further, because P is a non-singular matrix, we also know that if P is non-singular matrix, then row space of PA is equal to row space of A. This is a result already I have just recalled before the proof. So, the reason P is non-singular matrix. So therefore, we have shown that RB is equal to RA, that is the row space of B is equal to row space of A. Next, now third, to prove fourth statement from the third. What is third statement? Suppose row space of A is equal to row space of B. We have to prove that row echelon forms of A and B matrices are equal. Now it is given to us that row space of A is equal to row space of B, right? And since AR matrix is obtained from A by applying the row operation, right? And let BR be the matrix obtained from B by applying the row operations. And also it is already given to us that RA is equal to RB, that is the row space of A is equal to row space of B. And now I'm going to use that important remark that we have read before the start of the proof. Let me recall that again. If A and B are two matrices of the same type, such that row space of A is equal to row space of B, and if C and D be the matrices in a row echelon form, that is, obtained from A by applying the row operations and obtained from B by applying the row operations respectively, then this C is equal to D. That is, the row echelon form matrices are then equal. Here also, if AR is in the row echelon form obtained from A by applying the row operations, and BR is the matrix in the row echelon form obtained from B applying the row operations, with the condition that row space of A is equal to row space of B, then this AR is equal to BR. That is, the row echelon form of A and B are equal. Here this AR is representing your C and BR is representing your D in accordance with that important remark which we have just already read. Fine. Alright. Next, it is given to us that AR is equal to BR, right? The row echelon forms of A and B are equal. This is given to us now, and we have to prove back the statement 1, that is B is obtained from A by applying the row operations. To this statement we have to reach. Alright. Now because these two matrices in the row echelon form are equal, and since this AR is obtained from A by applying the row operations, and this BR is obtained from B by applying the row operations, therefore, there exists a non-singular matrix, let's say P and Q, such that AR is equal to PA and BR is equal to Q into B, right? Now because P is non-singular matrix, I can write from here A to be equal to, yes, P inverse into AR, which is further equal to P inverse. What is AR? It is given to us that this AR is equal to BR. So writing here BR. Further, this is equal to P inverse. What is BR? It is Q into B. Right? Let's take this together. So this implies A is equal to P inverse Q into B. And because P inverse Q is non-singular, now as P and Q is non-singular matrix, so P inverse Q is also your non-singular matrix. So we get a non-singular matrix P inverse Q, which is multiplied with B, and that is equal to this A. So for this existence of this non-singular matrix P inverse Q, I can write further that this B is obtained from A by applying the row operations. Why? Because here P inverse Q is non-singular matrix, hence the result. So we have shown that all these statements are equivalent. Alright, thank you.